that's Cartesian or polar. So for that reason, if there's no subscript, you should assume it's Cartesian, and if it's polar, you should explicitly indicate it. So there's a transformations between polar and Cartesian here, not left and right, but top and bottom, and we went over all of these complications with the tangent. Apparently recording me while he's absent. Coulomb force magnitude. I said specifically that you've got to be careful. There are absolute values you need to put over the charges because this is a magnitude, so the version of the book is strictly incorrect. K is just some numerical constant that sets the scale of how strong the Coulomb force is. These are the amounts of charge, and this is the distance between, R is the distance between the two charges, but it's squared. Now this F, because it's a magnitude, could be either F1 on 2 or F2 on 1. The magnitudes will be the same, and from Newton's third law, they should be pointing in opposite directions, no matter what the charges are. And getting the direction out of the magnitude, you actually extract that from similar triangles. That the triangle that the force vector makes and the triangle that the separation vector makes are in fact similar triangles. So if I, for brevity, call the vector from 1 to 2, which is R, and the vector and the force vector F, assuming that these have the same sign. This is, I didn't put in signs, but assuming that they're both the same sign, for example, plus and plus, then this force vector is pointing this way, but it would be the same if they're minus minus. And the angles are the same. Now this is only if they're plus and plus, so they're pointing in that direction. In general, if the signs are different, you may have to put in a plus or a minus in front of either one manually. Again, there are versions of this where you don't have to do it manually, but instead it gives it to you automatically. But just under this assumption that we don't have to put in any signs manually, this is, the angles are the same, so cosine of theta is x over r, but it's also fx over f. Sine theta is y over r, or also the y component of the force over the full magnitude of the force. So then, if the force vector is two components, or again, the plus and the minus, you have to put in manually, and it's not a part of this. You can express each Cartesian component in polar form, but then observe that cosine and sine can be expressed as not a ratio just of f of x and f, which is what I used there, but also in terms of these quantities for this triangle made by the displacement vector, separation vector. So then, at long last, you finally get plus or minus f times x over r, and then plus or minus f y over r. And you have to do this for every pair of, well, if you want to get the net Coulomb force on a single charge, you have to look at all of the magnitudes of the forces and all the force vectors of every other charge on that one charge. Okay. Well, you have to put in those signs manually. Okay, so let's do an example. I'm going to just do a very simple, typical example of this. Goes one step at a time, and I'm going to see if I can pick some good signs. Let's see what I want to do. Yeah, okay, I'll just make it. I'll make it visually and conceptually simple. Okay, so I'm going to put the main charge that we want to talk about at the origin. Just to keep things simple, so that when you then go and do more complicated ones, you'll pick up where this left off. But just to keep it really simple, let's do it like this. I'm going to put a bunch of charges over here and here and here. Okay. Okay, so let me say that this is the 3, this is 4 away, and let me say that this is charge Q1. Let me say it has charge, I don't know, positive 1. Let me say that this is charge Q2, let's say it has charge negative 2. This is charge, let's say Q3. Let's say it has charge positive 2. And let's say this one is charge Q4. And this is charge, I don't know, positive 1, let's just say. Okay, and let's say we want to know what is the net force on Q1. So the way we do this is we have to do this whole process to find this for every pair of charges on Q1. Yes? What? No, oh, sorry, I didn't draw it very well. So it should be directly above. So coordinates of Q2 should be 4, 0. So this point is 4, 0. This is point 0, 0. This is point 0, 3. And this is point 4, 3. Yes? Negative 2, that's the charge. Negative 2 coulombs, for example. I'm just dropping the units. Negative 2 coulombs. This 3 might be meters, for example, but it's negative 2 coulombs. Okay. So first, before we do anything, let's just get a bearing on what we should expect the answers to look like. So let's think about the force. Let's just say that Q3 exerts on Q1. They're both positive, and so should Q3 be pushing or pulling on Q1? Should be pushing. Okay, so yes? So likes repel, opposites attract. Okay. So if Q3 is pushing Q1, in what direction should the force vector be on Q1? It should be straight down, that's right. So first let me draw this arrow here. This arrow is F, I'll say 3 on 1. Okay, it's good to write, I know it's long, but it's good to write that so that it's clear, yes? Yeah, it's standard that if you have a number and you don't put plus in front of it, it's positive. Yes?
So, I noticed that your notation in the book is different, and I
Yeah.
wanted to understand.
Yeah, so the book might write 1, 3, is that what you're referring to?
It will say like on 3 by 1 instead of
Yeah.
by 3 on 1.
Yeah, I understand. So the book does a lot of things that I don't like. I'm doing this in a way so that when I write it, it's as brief as possible. If you want to, you can write on 1 by 3. You can do that. You can do by 3 on 1, you can do 3 on. I'm just doing this because this is as short as I can possibly write it because I have to write it manually every time. You can do it whatever way you want. So for example, a common similar issue is, let's say you have a velocity vector, and it's a function of time, and you have some vector v, which is considered the final one, and then you have some vector v naught, which is considered the initial vector. Okay, so the question becomes, well, clearly V has Vx, Vy, but when you write V naught, do you write V naught comma X, V naught comma Y? Or do you write Vx comma 0, Vy comma 0? Okay, it's your choice. The book does this. I do this. I do this because this makes more sense to me. I have a vector, this is what the vector is called, and then I tack on that's x, that's the component of that vector. The book, however, likes to think that there is some vector v, and then tacking a 0 on the end means the initial value, but I think that's an abuse of notation, because you do not use a subscript to refer to time generically. Okay, so this is just different choices. You're allowed to do whatever you want to do. You can change it, you can use notation. You don't have to use this notation. You can do whatever you want. I'm just showing you the way that I think personally is the fastest and easiest and clearest way to write it. If you disagree, if you have an alternative way of writing it, you can let me know. You can choose to do it your way. Does that make sense? Is that a question, sir? Okay, so just so that this is not confusing, I'm going to erase this. Oh, what happened to the signage sheet? Okay, you put it right there. That's a good idea. Okay. So if you didn't already, before you leave, please sign it, because I have to do verification of enrollment. Okay. So anyway, so this is 0, 0. This is, so we're doing this. So this is 3 on 1 is down. Okay, so now let's go to Q2 and Q1. Q1 is positive charge, Q2 has negative charge. So is Q2 pulling or pushing on Q1? It's pulling. So in what direction should it be pulling? Get to the, say it this way. Now this is positive and this is negative. Opposites attract. Okay, opposites attract. So in what direction so if it's pulling, Q2 should pull Q1 to the right. It's attracting, right? This is pulling on him to the right. You got it? Okay. So then this force vector is F2 on 1, and it should be pointing to the right. Now this up, down, left to right is going to affect which signs we put in manually. Manually, okay? Those are all manual. But it's easiest for us to assume that everything is positive, and then you put in a minus sign if you have to. So for example, for this one, we know that the force vector has to be purely in the y direction and down. So for this guy, 3 on 1, this should be 0 and a negative number. For 2 on 1, even though this is a minus charge here, the vector is positive and then 0. That's why it's very important that you take absolute values so that this is properly just a strictly non-negative number. Okay, now for the challenging one. Q4 on Q1. Okay, yeah, so are they pushing or, yeah, what do you think?
So it's
Pushing
pushing it away.
it away.
So it'll be on the
That's right, that's right. So along the axis, there will be a vector pushing away. And it's probably going to be kind of small because the charge is smaller than the other two, and it's farther away. But I'm going to draw it with an uncharacteristically long vector here, and this is 4 on 1. Okay? So for 4 on 1, I did this on purpose so that we know that we have to manually put in a minus and a minus, manually when we're done. However, for the purposes of our calculation, I might actually draw the vector over here. Or, whoops, maybe not. I might, just to make it similar to this diagram, but it doesn't matter because Newton's third law says that this is that and that's that, so it's, again, much like what sorry, what's your name again, sir? Kamani said, maybe it's best to not worry about angles that are greater than 90 degrees. You want to make two triangles all acute, and then manually put in signs. That's kind of the game that we're playing here. Okay. Sorry, I'm very bad with names, and I will keep asking. So let's do this one step at a time. First, we're going to do Q3, then we'll do Q2, and then we'll do Q4. And then when we're done, we have to add them all together. Okay, I picked the numbers 3 and 4. Why did I do that? Who knows why I picked the numbers 3 and 4? That's right. It's a 3, 4, 5 triangle. I know that the length of this is 5. Okay, so I know that when I do it divided by r here, I'm going to get a 5 and not like a square root of 11 or something like that. Okay, but generically what's going to happen is the magnitude is going to have an r squared, which is going to be okay. And so there's going to be an r squared lingering around in here, but there's going to be an extra 1 over r right here, which could be like a square root of 11 or something. So generically, the final answer is going to be r to the, it's going to be r cubed. Okay, or the 3 over 2 of the sum of the squares. So it's going to be an ugly number because of this r left over. It's going to be a square root typically right there. But I don't want that to scare you just yet, but just be aware that this r is typically going to be an ugly square root. Okay? Just be aware of that. That's typical. Okay, let me just so that I see some people puzzling over that. This r will typically be the square root of some number in the denominator. So you should expect to see that. You do not see a square root in the denominator there. Maybe you did something wrong. Okay, let's just get to it. Okay, so let's do 3 on 1. Okay, so first step, let's calculate the magnitude. Now for this also, I don't care about what k is, so I'm just going to leave it. I'm going to just factor out the k. I don't really care about that. So this is f equals k times absolute value of q1, q3 over r squared. I'm also just going to call it r, even though I've made different r's. This is r1 to 3. I'm going to avoid putting all these subscripts in when I'm doing each calculation because it'll be a little too messy. So we'll do it each separately and then put them together. Okay, so what is the distance? This one's easy. So the distance between this point and this point, you don't have to do Pythagorean theorem. You just see it right away. It's 3. It's 3 away. So 3 squared is 9. And Q1 is 1 and Q3 is 2. So it's 2 up top. So we've got k, which I don't care about, absolute value 1 times 2. Okay. And then this is over 3 squared. So I've got k 2 over 9. Okay, not too bad. Now we have to now, we don't really have to do any of this cosine, sine, similar triangles business because, well, let's just put it this way. We know that the magnitude of the vector has to be equal to the absolute value of the y component because the entire vector is pointing in the y direction. Okay, and another way to say that is that the angle it makes with the axis is negative 90. And cosine of negative 90 is 0, and sine of negative 90 is negative 1. Or equivalently, you can take Kamani's method of going from 0 to 90 and thinking that it's sine of 90 is 1, and then manually putting in a minus sign because it's pointing down. Okay, so this means you can straight away write that this force vector is 0, comma 1 of negative k 2 ninths. Okay, cool. And then these are newtons. This is all this thing is newtons, but I don't really care about the k value because it's not no ugly number, so I don't care. So if you want to, you can also factor out k. You can write it as k times a scalar. Remember, you can rescale a vector. Okay, you can just multiply that. You can just pull it out. Remember that rule of if I have a vector and I multiply it by a scalar, I just distribute it almost as if it's a polynomial. And these are components of the polynomial. Okay, good. Next one. Let's use up all the space we need. 2 on 1. So yeah, about that confusing thing about 3 on 1 or 2 or 1 on 3, it's important also to bear in mind that often on top of that they don't even say which is which. So sometimes you'll have just 3 comma 1 and you have no idea which way that's pointing. That's very bad, okay? So this is why I mean, if you're comfortable with that, that's fine. But I recommend don't ever do that because you're not going to know by looking at your calculations which convention you took. And furthermore, sometimes they don't even put the comma in there, and they'll just do 3, 1. This is common for matrices. It's so common that it's always used. I never use it because I don't ever want to use ambiguous notation. So I will always use non-ambiguous notation wherever possible. Okay, so now we've got, let's do the magnitude again. Again, I'm calling it F, not, with the subscript. Absolute value of K1 or Q1, Q2 over R squared. I'm not putting in the subscripts here. So let's see, Q1 is 1 and Q2 is -2. So absolute value of 1 times -2 and divided by R squared. You don't have to think too much about it. The distance is 4. 4 squared is 16. It's all right. So this is 4 squared. And now we've got k times 2 over 16. And if you want to, you can, simplify it and get k times 1/8. That's fine. For generic problems, you'll find that there's always going to be an r cubed in the denominator, and so you kind of want to factor out an r cubed, and it'll have all the square roots on top. But let's not get into that. Okay. Now for one of these manual signs that we have to put in. Okay. We know that, well, actually the opposite. We know that 2 on 1 is actually this way. So even though this is a minus and this is a plus, there are no special minus signs we have to put in. It's just all in the positive direction, and in the positive x direction, and nothing in the y direction. So the answer is k 1/8, comma 0. Okay, that's the full force vector of 2 on 1. Now for the tricky one. Now for the hard one. Now we're going to do what do we call it? 4 on 1. So F, K, absolute value of Q1, Q4 over R squared. It's a little trickier. So K, so Q1 is 1 and Q4 is 1, so it's 1 times 1. And now I'm going to write this explicitly as the sum of, maybe I shouldn't do that. Maybe I should have this okay, this one's already going. I've grown to like chalk because it's good to the last one. The markers are not. So in this context, look at this one. In this context, R squared is x squared plus y squared. And the x component is 4 and the y component is 3. So we've got 3 squared plus 4 squared, okay, which is 9 plus 16. 9 plus 16 is 25. So when I take the square root, I get that r is 5. Now it's not useful now, but it will be useful in a moment. Okay, so we have r. If we want r squared, we can just put 25, well, we put 5 squared. we've got k times 1 over 25. You can already see that by being just a little farther away, the strength of the force is much smaller. Okay, 1 over r squared decays very fast. Just a tiny increment away, and it's much weaker. Okay, now we're going to play, now this is the hardest one, this is the scary one. Okay, so we'll go very slowly. Okay, I'm going to write it manually. I'm going to write it out. Fx, x over r, Fy, y over r, and we're going to put in plus or minus. We're going to make all these choices. Oh, up. No, there's no subscript. Oops. Plus or minus, plus or minus. So, yeah. We're putting in plus or minus, okay, I see that there was something else that I did this wrong. Okay, so following Kimani's method, if all of this is assuming that the angles are between 0 and 90, that means that these also have to be strictly positive. Okay, sorry. Now, of course, there is a more advanced version. There is a more advanced version that you don't have to do all this manually, taking absolute values and then putting in plus or minuses. But unfortunately, maybe this is the best way to do it, right? So we're doing Kimani's method of acute triangles that can be upside down or back and forward, and then putting in the minus signs based on whether they point back or forward. Okay, so apologize about that. That was another simplification. So let's now put it in manually. Okay. So is the x component of this vector pointing in the positive or the negative x direction? Is this pointing in the positive or negative x direction? Negative. Okay. So we want to put in, this is negative, then f, k 1 over 25. Now times the absolute value of the separation, because strictly speaking, this part here is actually not 4, it's actually negative 4. Because if you go from here to here, you're going in the negative direction. Okay? But it doesn't matter. It doesn't matter, we're doing a method of just, Lonnie's method, so it's easier and more straightforward. So we can also write as negative 4 absolute value over r. And r is 5. No weird square roots, because I picked it so that I can take the square root of 25. Okay? But now notice I have 5 cubed. That's typical. Okay? Now let's do the y component. Is the y component positive or negative? It's negative. So we'll manually put in a minus sign. Okay. 1 over 25, then times absolute value of, it's really negative 3 because you're walking back, but it doesn't matter. Take absolute values, you put in all the signs you put in manually because you know the direction in which it's pointing. Okay, now I'm going to simplify a little bit. We got negative k, I'm going to keep the negatives red so that it's clear that you put that in manually. And then it's an absolute value, so it's 4 over, let me just call it 5 cubed. Let me just call 5 cubed, not 125. And then comma minus k 3 over 5 cubed. Okay. Now it's a little ugly. Remember, I can factor out common scalars. I'm going to factor out, I don't know, negative k over 5 cubed. That's just the way I like it, so that there's less ink for me. Negative k over 5 cubed times 4 comma 3. Okay, that is the final vector. Now, just like with the force table lab, you have to add them all up. Now, yeah, you know, I could play all these games with multiplying, dividing, and simplifying denominators, but let me not do that. Let me just keep it as is. Just keep it as is. So now I will write it as net on 1 is equal to 2 on 1 plus 3 on 1 plus 4 on 1. Now if you don't like this, you can do what the book does and just break it up into x and y pieces. This vector problem is entirely equivalent to a pair of scalar problems, which is f net on 1 in the x direction, which is the sum of just the x components. And I'm going to write it all out. And then you can just also add the y components. But we use vector notation to actually just simplify it so we don't have to write as much. All we're doing is the x component of the net force vector. The net force vector is going to be, so you got 1 year, 1 year, 1 year. Probably the net force is going to be something like, it's probably going to point kind of in that direction a little bit. It's probably going to be something like the net vector. Net on 1, something like that. So what we do is the x component of that is going to be this thing plus, plus this thing plus this thing. And then the y component is going to be this part plus this plus this. That's it. So just so that I don't have cluttered notation, let me just separate the x and the y parts. F net on 1 in the x direction. Let's just write it out. All right, 0. Okay, 0 plus, let me put them in parentheses too, just so it's clear, plus k times 1/8 plus negative k 4 over 125. All right, just write it that way. Negative k 4 over 125. Okay, you can immediately see how just a little bit farther away is a big deal. This is a minus sign, so it is going to lessen the amount by which this is pulling, right? Because this guy's pulling, but this guy's pushing away. But he's farther away with a smaller charge, so he's not really pushing away by that much. Okay, so the x component is, let me just factor out k times 1/8 minus 4 over 125. That's a horrible number, right? It's horrible, but that's just what it is. You can get a decimal expression or whatever, but that's the exact answer. Now let's do f net on 1y. Okay, so we got this guy plus 0 plus this guy, or him. So we got, negative k, negative k times 2/9 plus 0 plus negative negative k times 3 over 125. Okay, and it's ugly, but notice that you only have minus or 0 because the net result is going to point in the negative y direction. So that is consistent with what we should have pictorially. Now if you wonder, I'll factor out the negative sign. Negative k times 2/9 plus 3 over 125. And that's it. That's the answer. If you wanted to write this out as a single vector, that vector right there, this vector has the form, and I'm not going to do it manually. Net on 1 has the x component k times an eighth minus 4 over 125, whatever that is numerically, comma, negative k 2 over 9 plus 3 over 125. It looks horrible, but we were able to get there systematically by breaking it down into pieces and then putting it all together. K is a particular number that you put in. It's horrible, and I don't know. Okay, is that good? Everyone clear on that? Got what I did. Okay, I'm going to leave this behind. We're never going to talk about it again. If you want to do more examples, I recommend that you look at the homework and you do it with your recitation instructor, or we can do office hours. I was thinking maybe do office hours today. I have to do double office hours this week because I